So, students, we are now going to discuss the inorganic chemistry group 16 elements section. In the previous video, we did complete the chemical properties that were related to group 16 elements. There are several compounds that are formed by the group 16 elements. They are O2, dioxygen, O3, ozone, SO2, sulfur dioxide, SO3, sulfur trioxide, and H2SO4, sulfuric acid. In this video, and probably one more part preceding this, we would be completing theories on these compounds. For each and every compound, we are supposed to know their structure, their preparation, their physical and chemical properties. This is the very next important concept which is supposed to be learned by us. Let us start with the first important molecule, and that is dioxygen. When we are talking of dioxygen, the very first thing that comes before us is the preparatory methods to produce dioxygen. Over here, there are two fundamental methods, laboratory methods, and apart from laboratory methods, you have industry methods, large scale methods. In laboratory methods, the first method is when you heat potassium chlorate in presence of manganese dioxide, it results in the formation of potassium chloride and the rest is dioxygen. Now the question comes, how could we name this as chlorate and how could we name this as chloride? The naming in chemistry and especially in organic chemistry depends on the oxidation states. So as and when we say that the oxidation state of chlorine is -1, we generally refer to chloride. But apart from -1, the other oxidation states of chlorine are +1, +3, +5 and +7. And among these, the one with +7 is named by perchloric acid containing this chlorine. Over here, when it is in the form of ion, we coin it as perchlorate. Similarly, chlorine with +5 is chlorate. Depending on this, we call it as potassium chlorate, 2 moles, in presence of manganese dioxide and heating gives potassium chloride plus our desired product dioxygen. This is the first method for the preparation or production of dioxygen. Coming to the second method is a very important method where thermal decomposition occurs. And whenever we use the term thermal decomposition, it is heating. Over here, there is a different combination of products that are obtained. Whenever you use silver oxide, in the other term, it is oxide of argentium. Then 2 moles of silver oxide undergoing the heating or decomposition results into dioxygen plus silver. And the same kind of mechanism is observed when you undertake mercury oxide in the form of mercuric oxide. Over here also, it is mercury plus dioxygen. So these are very simple laboratory methods that can be implemented or executed for the preparation of different dioxygen molecules, different in the sense of mole ratios or stoichiometry. Still moving further, in the decomposition reaction set, If I say Pb3O4, mind it very well, it is beta plumbus or plumbic oxide, because the Pb over here, whenever you will calculate its oxidation state, it will be fraction which comes when a plus 2 and a plus 4 Pb combine. So this plumbus or plumbic oxide undergoing decomposition results in the formation of dioxygen. And a similar reaction is happened when plumbic oxide PbO2 Pbs plus 4 oxidation state. Remember very well, when Pb is plus 2 it is plumbus, and when it is plus 4 it is plumbic. It also undergoes so plumbic oxide converting to plumbus oxide and giving dioxygen. How confidently could we speak this? Because over here Pb is plus 4, over here Pb becomes plus 2. So lead gets reduced and it oxidizes someone else. Henceforth you are getting dioxide. So these are the very two popular methods for the preparation of this important products, that are plumbic oxide from plumbus oxide from plumbic oxide and dioxygen. And the first reaction where potassium chlorate got converted into potassium chloride. Moving in the same direction, if I still go further, I could come up with few other products, or to say few other reactions, where if hydrogen peroxide undergoes a reaction, it gives me water plus dioxygen gas. Over here hydrogen peroxide is 2 moles, so it's always in an aqueous form because we know it is either 30% or 40%. It gives you liquid and gas. This is how third important reaction occurs. So these are the three reactions which are lab scale reaction. They happen in laboratory. But when we go for a higher scale reaction, that are industry based reaction, what do we come across? On large scale, it is prepared from water or air. Electrolysis of water leads to release of oxygen and dihydrogen at anode and cathode respectively. Over here it is cathode first because it is hydrogen first. Remember, whenever water is electrolyzed, it gives you dioxygen and dihydrogen. This is how it works. So these were few preparatory methods where you could fetch up with these products. Moving in the similar direction, properties. Dioxygen is a colorless and an odorless gas, and it's soluble in water. 3.808 centimeter cube in every 100 centimeter cube means nearly 3%, which is sufficient for the aquatic life to survive. It liquefies at 90 Kelvin and freezes at 55 Kelvin. It has three important isotopes: oxygen 16, 17, and 18. You might be knowing, if not, remember very well, this is used when you prepare heavy water, and it is also used in isotopic labeling. I would urge you that as of now you just remember these names, because in the same year of your study you are going to learn these two things very detailed. So I will not waste any time over here. It is one of the component in heavy water, and it is used as one of the parameter in isotopic labeling. Moving in the same direction, if we go further, we can see that O2, according to the MOT theory of your junior class, is paramagnetic by nature. Total 2 unpaired electrons are present in the pi star 2py1, pi star 2pz1 type of orbits, orbitals. Sorry, if you remember. This is how it is paramagnetic by nature. So remember very well, dioxygen is paramagnetic by nature. Dioxygen reacts directly with nearly all metals and some non-metals also. It combines with other elements and often gives a strong exothermic reaction. Here we are going to see such reactions. If you see over here, when it combines with dioxygen, it forms calcium oxide. If it combines with 4 mole of aluminium, it forms aluminium oxide. If it combines with phosphorus, it forms phosphorus pentoxide. Over here, I'll be stopping for a minute. The reason is to make you understand the structure of P4O10. Remember this important structure. It might come somewhere in your journey of chemistry. So you must remember this structure. You very well know that phosphorus is a pentavalent element or an atom. Here 4 valencies are completed for phosphorus, and now we are going for the fifth valency of phosphorus. This point is not an intersection. It is an overlay of two bonds. If you look like this, you will observe that both the pens are touching each other. But if I'll move like this, you will come to know they are not touching. Over here also the same thing happens with this POP bond and that POP bond. They are overlaid on each other. So remember this structure very well. Moving further, you have C plus O2 gives CO2 and some popular reactions which you have already done. But the two reactions at the bottom, that is 2SO2 plus O2 in presence of V2O5 gives 2SO3, is very important reaction because the catalyst is vanadium pentoxide. V2O5 stands for beta vanadium pentoxide, and on the contrary, it is also a popular process known as contact process. Still moving in the same direction, 4HCl plus O2 giving you CuCl2 resulting into 2Cl2 plus 2H2O. So this is how it works. 4 moles of HCl plus O2, CuCl2 gives 2Cl2 plus 2H2O. So these are some fundamental things that we needed to discuss. Going to the uses of dioxygen, I could say that in addition to its importance in the normal respiration and combustion processes, oxygen is also used in oxyacetylene welding. Now, what is oxyacetylene welding? We have seen some laborers making a welding of iron or steel even. They use two types of gases. If you will see the flame that is coming out from his burner, it will be bluish in color. But if you look into the chemical composition or the chemistry of that blue color, it is a mixture of oxygen and Hc triple bond CH, that is ethine, which is also known as acetylene. And therefore this mixture is called oxyacetylene, where oxygen is used for combustion. आग के लिए हवा चाहिए, air चाहिए, O2 चाहिए, and Hc triple bond CH acetylene is a fuel. So this is how these are few of the uses that are given here. Please go through them. We have also discussed these chemical properties, the physical properties, and the preparation of dioxide. Now we are moving towards few other simple oxides and theory related to it. Over here, we will be writing, or we will be rather discussing the oxides of metals, the oxides of non-metals, and even when required, we will still move a step further by discussing their properties. What properties? Their acidity, their basicity, their oxidation power, like this. So, whenever it comes to oxides, most of the elements form oxides. But what about non-metal oxides? What about metal oxides and what about their properties? We'll look over here. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. We can see that MgO, Al2O3 are oxides. These are simple oxides where the oxidation state of that element other than oxygen is whole number. Whereas in Pb3O4 and Fe3O4, these are also oxides, but the oxidation state of Fe and Pb will not be a whole number. It will be an integer. Whereas over here it will be a whole number. So these are simple oxides and these are mixed oxides. These are the combination of two different oxides. Pb3O4 means PbO plus. If you will go, it is Pb3O4 means 2 moles of PbO plus PbO2. So it's a mixed oxides. Over here it is Fe2O3 plus FeO. This is how it works. Simple oxides can be classified on the basis of their acidic, basic, or amphoteric character. An oxide that combines with water to give an acid is always treated as acidic oxide. Remember, an oxide that combines with water to give acid is always treated as acidic oxide. SO2 plus H2O, H2SO3, sulfurous acid. SO3 plus H2O, H2SO4, sulfuric acid. And very important, CO2 plus H2O, H2CO3, carbonic acid. So all these SO2, SO3, CO2, even Cl2O7, N2O5, all these are acidic oxides. Also remember one more important chemistry I'll tell you. Mostly metal oxide are basic and non-metal oxide are acidic. Non-metal oxides are acidic. Over here if you check sulfur, carbon and even nitrogen is given, Cl2O7, N2O5, all these elements are, yes, non-metals, and the oxides of non-metals are generally basic. Still moving further, as a general rule only non-metal oxides are acidic, but oxides of some metals in high oxidation state have acidic character. What they have written? Non-metal oxides are acidic. What I have already mentioned here. Non-metal oxides are acidic. But there are few other which are acidic. They are exceptional. Mn2O7, V2O5, and you have CrO3. So Mn2O7, V2O5, and CrO3 are few other also being metal. They must be basic, but they are not. They are exceptionally acidic oxide. But what about other basic oxides? They do exist. Barium oxide, calcium oxide, oxide of sodium. All these oxides are metal oxides, and metal oxides are very good, basic in character. So friends, remember these concepts very well. They are very important concepts. Still going in detail. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. Dual means they are both acidic as well as basic, amphoteric. They show characteristic of acid as well as base. Such oxides are known as amphoteric oxides. They react with acids as well as alkali. There are some oxides are neither acidic nor basic. See, when both acidic and basic, you call it amphoteric. But no acidic, no basic, you call it neutral. Al2O3, remember very well, is an amphoteric oxide. Al2O3 is an amphoteric oxide. Whereas N2O, NO, CO are neutral oxide. Remember them? N2O, NO, CO are neutral oxide, whereas Al2O3 is amphoteric oxide. Amphoteric means it reacts with both acid and base. And you can see in the bottom, there are two important reactions for you to remember. Al2O3 reacts with acid, Al2O3 reacts with base. And as it reacts with both, it is amphoteric by nature. So, this was second important thing that we must imbibe over here or we must learn over here. This was all about dioxygen and the oxides. You have on the other hand ozone over here, which is also one of the very important topic. So let us start with ozone. As you all know, ozone is O3 and it is always made up of only the atoms of oxygen. It is allotrope and such allotrope are only made up of a single type of atom. And when it comes to ozone, remember very well, represented by O3. I will also coin it in a different way. It's an oxide of oxygen. When O combines with O2, OO2, it is O3. Ozone is an allotropic form of oxygen. It is too reactive to remain long in the atmosphere. At a height of about 20 kilometers, it is formed from atmospheric oxygen in presence of sunlight. The ozone layer protects the earth from, as we know, the UV radiations, the ultraviolet radiations. Preparations. A very simple reaction where dioxygen gets converted into ozone. When a slow, dry stream of oxygen is passed through a silent electrical discharge, dioxygen gets converted into ozone. Over here, you need to add energy as you are passing a spark, silent electrical discharge, you will be adding energy, and that energy is 142 kilojoule per mole. So fundamentally, it's an endothermic reaction. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use silent electrical discharge in its preparation. If concentration of ozone greater than 10% are required, a battery of ozonizers can be used and pure ozone can be condensed in the vessel. Properties. Pure ozone is a pale blue gas, dark blue liquid and violet black solid. You can see it is in gas, it is in liquid, it is in solid. Also a very interesting thing, as we went from gas to liquid and from liquid to solid, the color intensity increased. And when we say the color intensity is increasing, it only happens when the molecules come more and more near to each other. So the blue got converted into dark blue and from dark blue into violet because diffraction phenomena is involved. Now moving further in the same aspect, if concentration rises above 100 ppm, breathing becomes uncomfortable. Remember very well. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results as a liberation of heat. That is entropy over here also increases. Enthalpy is negative. This can be seen from a reaction given over there. O3 results into O2 plus O. This O, which is always single, it is very difficult to get, but when you get, it is called nascent. Nascent, nascent oxygen. Remember these reactions very well. Now moving in the further direction, you see it is written over there that PBS when combines with 4O2, 4O3 ozone, it results in the formation of PbSO4 plus 4O2. So this is a chemical reaction of ozone. So ozone fundamentally acts as an oxidizing agent. You can see over here PbS, no oxygen. PbS has oxygen. So if an element gets oxygen, it is called to be oxidized. When ozone reacts with excess of potassium iodide solution buffered with borate buffer, iodine is liberated. On the left, you are having I minus. On the right, you are having I2. Over here, it was minus to oxidation state. Over here, it is 0. So you are taking an oxidation reaction. So ozone over here also acts as an oxidizing agent. This explanation is for the second reaction given over there. So this is how we calculate or we prove that ozone is an oxidizing agent. And this reaction help in calculating quantitatively iodine content. Experiments have shown that nitrogen oxide combine very rapidly with ozone and therefore possibility of nitrogen oxide emitted from the exhaust system of supersonic jet aeroplanes might be slowly depleting the ozone layer. This can be seen over there at a very heated atmosphere where ozone combines with NO, it results into NO2 plus O2. No way you are getting dioxygen at a very elevated height where no human beings live, but you are depleting ozone. That is a problem. Another threat to this ozone layer is probably posed by the use of freons. You know what are freons? Chlorofluorocarbons. Freons are beta chlorofluorocarbons. Where are they used? Where are they used? Chlorofluorocarbons are used in air conditioners and refrigerators. The two oxygen bond lengths in ozone molecule are identical. See, ozone has a resonating structure. One structure, second structure, and from these two structure you get a new structure where the bond length is 128 picometer and the bond angle is 117 degree. So this is the resonance hybrid of these two structures. If you look into the uses, it is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching oils, ivory, flour, starch, etc. It acts as an oxidizing agent, and also it is a very important content in the manufacturing of potassium permanganate, that is KMNO4. So friends, this is how we are concluding, or we are on the verge of concluding this part of the video, where we have discussed dioxygen, its preparation, its chemical properties, and uses. Then we went with simple oxides, its basic nature, its acidic nature, Al2O3 has an amphoteric nature, and few neutral oxides. And then we discussed ozone. So this is how we are probably completing the compounds that are related with oxygen. And in the upcoming video, we will be discussing the compounds that are related with sulfur. There are only two compounds in your syllabi: sulfur dioxide, that is SO2, and H2SO4, that is sulfuric acid. So rest we'll keep for the next video. We'll be just stopping this video now. If you have any queries, feel free to contact me. So in the upcoming video, I can start with the upcoming topic. Thank you.